In the last section, we talked about exponential growth functions, and today we're going to be talking about exponential decay functions. So when I think about growth, I think about something that's increasing, something that's growing. Well, decay is kind of the opposite, where I'm going to start with some amount, and that amount is going to decrease. It's going to lower at each step of the way until it approaches zero, because we can't really decay to something that's negative. We can only decay to something that's maybe zero. So what might that look like? Well, let's compare f of x equals 1/2 to the x and f of x equals 1/10 to the x. As we know, anything to the power of 0 is going to be 1. So let's start there. This will be 1 here, and this will be 1 over here. 1/2 to the first power, well, that's just going to be 1/2. 1/10 to the first power, that'd be 1/10. And as we increase, so x is 2 now, this is going to essentially say what is 1 to the second power over what is 2 to the second power. So this will be 1 over 4. And then 3, 1 to the third over 2 to the third. This will be 1 over 8. Over here, we'll get 1 over 100, 1 over 1,000. And then as we go negative, this will be 2, 4, then 8. See the pattern here? And then for 1/10, as we go negative, this will be 10, 100, and then 1,000. All right, looking at the graph of each of these, it looks like this. So this is 1/2 to the x, and this is 1/10 to the x. So a couple questions we have about these are, in what ways are these functions similar? And how do these functions differ? So both are decreasing. And they even have kind of similar curves. But I would say that 1/10 to the x is decreasing much faster. This curve here is much sharper. Okay, so I'd say but 1/10 to the x is decreasing or falling much faster. How are the end behaviors trending? Meaning, as this goes to infinity, what is happening? So as this is going to infinity, as x goes to infinity, y goes to 0. So y is approaching 0. And here, same thing, as x approaches infinity, now it looks like it hits the x-axis, but it's actually just going to barely scrape by and not actually hit the x-axis here. So how are the end behaviors trending as x approaches infinity? I would say y approaches 0. Okay, and I would say that this goes toward the horizontal asymptote. Okay, and then transformations. This will be very, very similar to everything else we've done with transformations. G of x equals a times b to the x minus h plus k. Okay, this is my standard form for an exponential function. Again, a represents my vertical stretch or compression. If the absolute value of a is greater than 1, the graph is stretched vertically. If the absolute value of a is between 0 and 1, the graph is compressed vertically. And if a is negative, the graph is reflected over the x-axis. So this would be a vertical reflection. B is the base of the function. So this will be what number is the base to that exponent. And x is the variable here. If it's negative x, then the graph is reflected over the y-axis. So this would be a horizontal reflection. H represents my horizontal translation. So this is shifting left and right. Again, because this is horizontal, it's kind of the opposite of what I would think. If it says x minus h, the graph is shifted to the right to that many units. If the translation is x plus h, then we're shifting to the left that many units. K represents the vertical translation. So this is shifting up or down. Vertical is intuitive. That makes sense. So if it's plus k, I go up that many. If it's minus k, I go down that many. Now, what is going to be different are my reference points. Reference point 1 is the same, h comma a plus k, same as exponential growth. However, the second one here, it differs from exponential growth in that here, this is going to be h minus 1, and then a over b plus k. So I want to remember that. My second reference point is h minus 1, then a over b plus k, which also implies that for exponential decay, reference point 1 is now going to be to the right of reference point 2. The horizontal asymptote, however, is still the same, y equals k. Let's do a couple examples. Find all reference points and asymptotes for the given functions. So this first one, I've got g of x equals 3 times 1/2 to the x minus 2, then minus 2 at the very end. So let's find what a, b, h, and k are. A is 3. So this is going to tell me that there's going to be a vertical stretch of 3. B, which is my base, is 1/2. H is 2. Don't be confused and put minus 2 here because the standard form says x minus h. So if this says x minus 2, then h is 2. This will tell me that there's going to be a shift to the right 2 units. And then I've got minus 2 at the very end, so k is negative 2. There's going to be a shift down 2 units. So then let's find a couple reference points. Reference point 1 is h comma a plus k. So filling that in with what we know, h is 2 comma a plus k would be 3 plus negative 2. Which means my first reference point is 2, 1. My second reference point is h minus 1, and then a divided by b plus k. So again, let's fill in what we know. H minus 1 would be 2 minus 1, comma, a divided by b, so that's 3 divided by 1/2, and then plus negative 2. All right, 2 minus 1, this will be 1, comma, 3 divided by 1/2. So that's the same as saying 3 times 2. That's going to be 6, and then plus a negative 2, that will be 4. All right, and then my horizontal asymptote is at y equals k. So this will tell me I've got a horizontal asymptote at y equals k is negative 2. With this information, let's create the graph and then compare to my original here. So blue will be just my regular exponential decay function without any transformations happening. And then the red one here will be what I've actually found. All right, let's do one more of these. Let's say I've got g of x equals negative 1 over 10 to the x plus 2 and then plus 8 at the very end. Again, let's find a, b, h, and k, and then reference point 1, reference point 2, and the horizontal asymptote. Here, a is going to be negative 1. Now, I don't actually have a 1 written here, but it's negative and then 1 over 10 to the x plus 2. So this implies that a is negative 1. That means that there's going to be a reflection vertically. B is 1/10. H is the opposite of what I see here. So if it says x plus 2, then it'll be negative 2, meaning there'll be a shift to the left 2 units. And then k at the very end is 8. So a shift up of 8 units. Let's find reference point 1 and reference point 2. So let's see, h comma a plus k. So that'll be negative 2, comma, a plus k is negative 1 plus 8. So this is negative 2, 7. All right, reference point 2, h minus 1. So this will be negative 2 minus 1, comma, a over b, so negative 1 divided by 1/10, and then plus 8 at the end. Negative 2 minus 1, that's negative 3, comma, negative 1 divided by 1/10. That's going to be the same as negative 1 times 10. So that's negative 10 plus 8. So negative 10 plus 8, this will be negative 2. Okay, then horizontal asymptote, y equals k. So this will be y equals 8. All right, then let's look at the graph. All right, blue is what it would look like without any transformations, and red is after the transformations that I've put on it. Let's do a problem where we do the opposite, where instead of finding function and then looking at its graph, let's start with its graph and then find the function. So here I've got a graph. It says use the graph to the right to find the exponential function of the form g of x equals a times b to the x minus h plus k. In this graph, I've got a few things. I've got a horizontal asymptote at y equals 4. And then I've got this curve here with 2 points identified, -4, -2, and -3, +1. The first thing I'm going to do is, given that the horizontal asymptote is always at y equals k, I'm going to say, well, this is y equals 4. So I've got a horizontal asymptote at y equals 4, k must be 4. All right, next. Reference point 1 is at h comma a plus k. Remember, for exponential decay, this is going to be the point on the right. So this will be -3, 1. Left equals left, right equals right. So h equals -3. And then a plus k is going to be 1. But we know that k is 4. So that means a plus 4 equals 1. Let's subtract 4 from both sides. A is equal to -3. The difference between these problems in this section and the ones in the last one is that you're not given a value for b. So you have to actually find what b is. Here we're going to use reference point 2 to help us with that. Reference point 2 is -4, -2. And we've got h minus 1 comma a divided by b plus k. Now, normally I would say left equals left, right equals right, but if I do the left part, h minus 1 equals -4, that's just going to help us solve for h again. So that's not helpful. What is helpful is the right side. On the right side, I've got a over b plus k, so this is going to be equal to -2. A over b plus k is equal to -2. Let's fill in what we know. A is -3, so -3 over b plus k is 4. This is equal to -2. All right, let's start solving. Subtract 4 from both sides. So we've got -3 over b is equal to -6. We'll multiply both sides by b. So we'll get -3 is equal to -6b. And then divide both sides by -6. B is equal to negative over a negative is a positive, and then 3 over 6 will reduce that to 1/2. All right, now I've got everything I need. A, B, H, and K. So the standard form is g of x equals a times b to the x minus h plus k. Let's go ahead and fill in everything. This will be g of x equals -3, parentheses, b is 1/2 to the x minus h. So we'll do x minus -3, so plus 3, and then plus k at the end, plus 4. Now I've got one more problem for us to do, and that's looking at a real world problem where I'm buying something and that thing is going to decrease in value over time. This often happens with things like vehicles, for example. Have to buy a vehicle to be able to get around, but the problem with that is whenever you make a purchase on a vehicle, more often than not, the value of that car, value of that truck, whatever, is going to go down over time just because new models come out, among other things. So here we're going to use the function f of t equals a parentheses 1 minus r to the t. You'll remember that in exponential growth, a problem in the real world sense used a times 1 plus r. So the difference between growth and decay is whether you're adding your rate or you're subtracting your rate. For growth, you'll add. For decay, we're going to subtract. Everything else is pretty much the same here. A is your principal amount, what you start with. R is your rate of decay. Remember, we want this as a decimal. So if it's 14%, then I'm going to do 14 divided by 100. That'd be 0.14. That's what I'm going to put in for R, 1 minus 0.14. And then T is going to be our time. So here I've got the value of a truck purchased new for $28,000 decreases by 9.5% each year. So the principal amount, what I paid originally, is $28,000. My rate of decay is 9.5%, so I'm going to take 9.5 divided by 100. That'll be 0.095. Then I can go ahead and plug it all in. So f of t equals a times 1 minus r to the t. This will be 28,000 times 1 minus 0.095 to the t. I want to know, when will this truck decrease in value down to $5,000? So I've already done that for you here. But what you would do using a graphing utility or Desmos or something is you'd plug this in. 28,000 times the quantity 1 minus 0.095 to the t. You might have to use x for a graph here, and you'll get this red curve. Then what I would do is separately, I would also graph just y equals whatever you're looking to find, the value at the very end. So y equals 5,000. And you'll see that those two are going to intersect. You'll have this curve and you'll have just a horizontal line. And where those intersect, the x value is how much time take. In this case, the value of the truck will reach $5,000 after 17.26 years, so a little over 17 years. You'll have a few problems like this, as well as all the other ones that we worked on in the assignment for this section.